So yeah, it's great to be at least virtually back to, I guess, Bonn, where I spent a number of years for my bachelor's and master's. So yeah, so what I'm going to talk about is this, like as the title alludes to, is this like bigger piece of vision, or if you want, of information geometric mechanics, but really the sort of more concrete piece of work that I'm mostly going to talk about is this, what I view as the first instantiation of this broader philosophy, if you will, which is joint work with my former student Richard Tsao, that we call information geometric regularization. And so the problem that we are addressing with this work is that of shock formation and gas dynamics, right? So whenever you have highly energetic gas dynamics, for instance, in astrophysics or in aerospace applications, the equations of gas dynamics have the tendency of developing so-called shocks, which are you see as these sort of like lines here in this Schlieren imaging on the right. Which are basically jumps in the state variables of the gas, so the pressure, density, velocity. And so what's very important is that even though from a macroscopic perspective, so here you see the Schlieren imaging of a shock arising from some detonation, on a macroscopic perspective, these looks like discontinuities. But then if you actually zoom in far enough up to something of the order of the mean free path of the gas, so for instance in air that would be a few microns, you see that of course the sort of residual viscosity of the gas is going to make these profiles again look smooth. And sometimes that is why I think this very much fits into the topic of this workshop on multiscale methods, is that really shock formation is a multiscale problem. So in principle, everything would be nice and smooth, but the problem is that the smoothness lives on scales that we cannot resolve in practice with our computational grids. And so somehow dealing with this shock simulation amounts or requires coarse graining the effect of the shock. And so to make things more concrete, we're going to use, at least for this talk, for most of this talk, we're going to use the compressible barotropic Euler equations. So of course, there are numerous sort of more sophisticated models of gas dynamics. And what I'm going to present is, in fact, is applicable to a wider range of equations of a similar type. But to keep things simple, we're going to restrict ourselves to that equation. And really, what you should take away here is the first equation is the conservation of momentum. The second equation is the conservation of mass. And so if you're not familiar with or like used to thinking about these conservation laws, it's even easier to think about them in one dimension, where you can think of this term on the right. This is the instantaneous flux of momentum and density that is passing through a point, right? So for instance, the instantaneous flux of momentum is the current velocity of particles times the momentum that they carry. So that's why you have the rho u squared. The instantaneous flux of mass is the mass of particles passing through there times the velocity with which they pass through. And then to determine the rate of change in a point, you simply take the difference between what flows in versus what flows out. And that's where these equations come from. And then you get sort of in the multidimensional case, this divergence is replaced by a divergence. And commonly, we think of the appropriate solution concept for these equations as so-called vanishing viscosity solutions, meaning that we say any gas is going to have some very small amount of viscosity. So that's why we're adding a viscous or dissipative term here to this equation. But then we tell ourselves that we do not want to actually rely on this viscosity because it is so small compared to the other relevant quantities. So we formally, as an idealization, we look at the limit of such solutions as we let the viscosity go to zero. And that is sort of our idealization of gas dynamics, that we imagine we have this sort of they have this very small viscosity and we keep decreasing it formally to the limit of vanishing viscosity, and that is what we consider our solution. And the goal of this is really to make sure that we do not cheat by somehow exploiting that viscosity and the resulting smoothing out of the shocks, because we want to remind ourselves that this viscosity is so small that we cannot rely on it for numerical purposes. And now, of course, if you want to simulate these equations numerically, the first thing we could do is we could just say, instead of letting our viscosity go to 0, we just choose a very small viscosity. But the problem with this is that if we choose a very small viscosity, we get these grid-sized discontinuities. And the moment we start using higher order methods that typically rely on fitting some kind of higher order polynomial to our solutions, we get hit with Gibbs-Runge phenomena that produce oscillatory solutions that are going to blow up. And of course, simply increasing the viscosity is not the answer either, because then we end up simulating very well something that is very different from the object that we're actually interested in simulating. And I mean, this is a very classical problem, how to, again, essentially coarse-grain the shock. And in some sense, the first approach was really to add a nonlinear diffusion to these equations. So what we are saying now is that we introduce as a numerical device, or if you will, as a form of homogenization of the shock effect, we're adding a nonlinear viscous term that is designed in such a way that it turns on only close to the shock in order to stabilize the numerical simulation, and then is trying to be as close to 0 as possible when there's no shock, to preserve the accuracy of our underlying numerical method. And of course, the name of the game is now that we're trying to avoid either our solution breaking down from too little viscosity that we're adding, or us sort of over smoothing our solutions by adding too much. And there's a gazillion different proposals for different parametric forms of this adaptive viscosity in order to try to strike this balance as well as possible. And so here I'm showing you one such example, which is where the viscosity is proportional to the spatial derivative of the velocity field, so the negative part of it. And now what we're seeing is that if we now choose different tuning parameter for the weight of this nonlinear viscosity, we see that the shock is spread out over a wider and wider region, right? So it's not an instantaneous jump anymore, but it's spread out. So that's good news. But one negative thing that we're already seeing is that the shock has so basically, even though we don't have a jump discontinuity anymore, we still have this kind of kink at the top of it, right? So we don't get higher order smoothness with this approach in general. And the second problem is that if we now look at instead of looking at a shock problem, we look at a different solution where we have a high frequency oscillation, for instance, due to sound waves or turbulence. And then we see that as we're increasing this parameter alpha, we're going to be more and more dissipative and spurious to dissipate this oscillatory structure. And so that's really the name of the game. And the challenge is to somehow distinguish between shocks where we want to replace the solution with something smooth and oscillatory structures that are not dissipating energy, but that we have to somehow distinguish from shocks so that we do not accidentally dissipate them out. And so now so far I've shown you this whole story in terms of nonlinear diffusion. There's also a closely related approach, which are called limiters, which instead employ nonlinear numerical methods that basically drop down to lower order approximations close to shocks, which then tend to be diffusive. So the in spirit is somewhat comparable to the approach of nonlinear diffusion. They are oftentimes practically quite useful, but there's still sometimes issues with numerical artifacts that arise from these nonlinear numerical methods. There can be spurious sensitivities if you're interested in differentiating through the solution, for instance, for design optimization. And finally, there's a certain type of technical debt that's associated with building our shock treatment into the solution into the numerical method, because it means that each time we want to develop a new numerical method, we have to sort of reinvent the wheel for how do we deal with shocks. Okay, and so based on both the prior successes and the limitations of it that I've shown you so far, there was always, if you will, a third approach or a third line of idea, which was maybe viscosity is not the right way of coarse graining the shock after all. Maybe there are other mechanisms to coarse grain the effect of shocks in compressible fluid dynamics. And so the first attempt of this was by Bart Federico Marston Mosseni West, who tried to use what sometimes called Lehrer regularization, which is closely related to Lagrangian average, Navier-Stokes Lagrangian average, Euler type models. But the problem is that their method did not achieve the right shock speeds. And so that makes it unfortunately not useful for numerical purposes. More recently, there's a line of work based on what's called, I guess we could call it Saint-Venant regularization, so ideas originating from the shallow water equation. But the problem with this approach is that if one solves it with a non-dissipative numerical method, it tends to produce these funky cusp-like singularities, which are interesting to look at, but are not physical. And so in the main part of this talk, what I'm going to present to you is what I believe is a solution to this problem of regularizing the compressible Euler equations with a different mechanism that does not rely on viscosity. And so here you see the equation. So the equation amounts to adding this scalar quantity sigma that is defined in terms of an auxiliary elliptic PDE, adding this to the physical pressure of the equation. And before I explain you where this equation comes from, I want to show you two little videos that hopefully convince you that this might be an interesting regularization. So the first is that if you now revisit our problem with the shock, we see that this regularization produces higher order smooth profiles. So it's not just that we're replacing the jump with some sort of steep slope, but really we are getting empirically and in some cases even theoretically provable higher order smooth profiles, which is of course great news if you want to use higher order numerical methods, fit these profiles with higher order polynomials. And secondly, even at this very large value of alpha to the right, where we're adding a lot of regularization, we see next to no dissipation for these oscillatory structures. So if I compare again to this viscous regularization from before that you see on the bottom, you see that even for a much smoother profile that we're replacing the shock with, we see next to no viscous viscous dissipation of the oscillatory structures, which we want to preserve, which is a very different behavior from what we see with these local viscous regularizations. Okay, so this is sort of the game plan is we want to derive this equation. And this equation is quite complicated. So I think it's fair to say it would have been pretty hopeless to discover it just by trying out a lot of different equations until one of them works. And so instead, there is a certain geometric, and as we will see, information geometric idea behind this equation. That's what I want to describe next. Okay, so in order to derive this equation, we're going to start with a very simplified case where we say that the pressure is zero, so the so-called pressureless Euler regime, and we're looking at the one-dimensional case. And in this case, it's quite straightforward to solve this equation using essentially the method of characteristics. So we define these particle trajectories phi t of x that record basically the path of a particle that starts in x. And now the particles, without the pressure, the particles don't interact with each other, at least before shock forms. And so they just travel on straight lines. And then we can write down the solution in pretty much closed form just by we get the velocity in a certain point by tracing it back to where is the particle that's passing through right now, where did it start, and what was its initial velocity. Likewise, to get the density in a point, we basically investigate whether around a point the particle trajectories are rather converging or rather dispersing. And that is encoded in the spatial derivative of this deformation map that maps sort of initial points to current positions. And now if we take this perspective in terms of this, as I mentioned, deformation map that maps this information phi t that maps initial to current positions, And there are really four interesting perspectives on how to reason about shocks. And so the first and maybe most classical one, that's what you see in the Evans chapter on hyperbolic equations, is that shocks form when these trajectories, which are now both particle trajectories and characteristics, collide, right? So that's probably something that everyone, or most people in this room, have seen before, this way of looking at it. Now we can also, instead, we can view the path of this deformation map on a manifold of diffeomorphisms, if you want to be fancy, right? So especially in the incompressible case, this way of looking at Euler solutions was pioneered by Vladimir Arnold. We view solutions of the Euler equations as trajectories on manifolds of diffeomorphisms. And now in the compressible case, we are not dealing with volume-preserving diffeomorphisms, but with general diffeomorphisms. And it turns out that we can view shock formation as arising from our sort of trajectory reaching the boundary of the manifold of diffeomorphisms. Because that is exactly what we do when we map two points to the two input points to the same output points, then our map ceases to be differentiably invertible, and so we've reached the end of being a diffeomorphism. We can also view it from a transport perspective by saying that shocks form when the push forward of our initial mass density becomes singular. So we form these atoms because without the pressure, particles are sticking to each other. And finally, and this last form is maybe the least well known, even though it is known in parts of the pressureless Euler community, if you will, is that we can view shock formation or even the definition of these deformation maps, we can view them through this minimization problem here. So we're minimizing a sum of this linear term, the first term, that basically rewards our deformation map for transporting particles in the direction of the initial velocity, right? So the more I move in the initial velocity, the smaller this first linear term becomes. But at the same time, we're adding a regularization because we don't want it to move the particles too quickly, too fast. So we add this quadratic term that rewards it for staying close to where it was. And so as time increases, we're sort of putting more weight on the first term that rewards it for transport than on the second term that rewards for staying there. And we can show just by taking the derivative with respect to t that this exactly recovers the pressureless Euler equation. And importantly, we have this one additional constraint, which is that we want our map to be monotone. In other words, we want it to stay differentiably invertible. And the shock formation exactly coincides with the point when this constraint is violated, or rather becomes active. So when we start getting a different result because of this additional constraint, then we would get in the unconstrained problem. Okay, so we have these four perspectives now on looking at this phi and what happens to it when shocks form. Now, what happens after the shock in a vanishing viscosity solution? In this first perspective on merging or like colliding characteristics, it turns out that particles collide, dissipate the maximum amount of energy, and sort of governed by conservation of momentum, merge with each other. In the second perspective, it looks like that we basically reach the boundary of our diffeomorphism manifold and then slide along the boundary of the diffeomorphism manifold. In the third perspective, we form these Dirac measures in the shock, and then we just propagate the Dirac measure. In the fourth perspective, we keep solving this minimization problem, just that now we solve it as a constraint minimization problem. And so again, the solution is going to be sticking close to the boundary, as is quite typical for inequality constraint optimization problems. Okay, so there's a lot of maybe background perspectives and so on and so forth. And so now we want to start to actually regularize this equation. We want to change the dynamics of it so that it becomes better behaved. And as a starting point, we're going to take the fourth of these perspectives, the optimization perspective. And so we remind ourselves that a very general principle for optimization are the so-called homotopy interior point methods. We basically say we have a linear objective and we're adding some kind of regularizer that we then decrease the weight of over time. And so here you can think again, the first thing is the linear objective that we think of optimizing, and the second term is the sort of a regularizer of our solution. And typically one would try to choose this regularizer in such a way that it preserves the feasibility of our point. And so more generally, one would use a so-called Bregman divergence associated to a certain barrier function. And now in the nominal problem, we are using the Bregman divergence given by the squared Euclidean norm and the squared L2 norm. And of course, the problem with that is that this barrier function is not strong enough to prevent us from reaching the boundary of our constraint set, right? It regularizes the problem a bit, but it is not strong enough to prevent us from reaching that point where the deformation map becomes singular. And that's not so surprising because this quadratic barrier function, nothing really special happens when the derivative of x becomes 0 here, right? So there's no hope that as we increase t that it would always prevent us from reaching the boundary. And so that's why in a more optimization literature, people would tend to use rather a barrier like this that has this negative logarithm of the quantity that we want to keep positive. And so this is how we can now regularize this optimization definition of our barrier function, of our deformation map, by adding this negative logarithm of the derivative. And that is what ensures that the derivative has to stay positive, because when the derivative becomes close to 0, then this logarithm blows up. And as a result, if we replace this Bregman divergence above, if we replace this from using the quadratic norm to using this quadratic norm regularized with a multiple of the negative logarithm of the derivative, we see that now our trajectories, instead of hitting the boundary, they asymptotically approach the boundary. And this weight alpha that we're using for the amount of regularization, that determines basically how aggressive we are in approaching the boundary of the constraint set. And if we pull back these sort of trajectories in terms of deformation maps, if we pull them back to particles, then we see that now in our regularized dynamics, instead of particles colliding and merging, they only asymptotically approach each other. And that's a very attractive feature for regularization of these equations, because it means that in terms of the long-time behavior, we are seeing the same long-time behavior as before, right? Because if you zoom out a bit, you see that all these particles are still kind of asymptotically approaching each other. But at the same time, because the particles never collide, we never actually form a singularity. So we now have a mechanism that prevents singularity formation while preserving the main features of the equation, which is of the solutions, which is sort of what we are interested in when trying to regularize these equations. Now the main challenge is that this minimization perspective is still a little bit artificial, you could say, for the compressible Euler equation, because it really only holds in this pressureless case in one dimension. So in some sense, it's a very it would be a very restricted thing. And so what we want to do now is we want to recover that same mechanism, but recover it in a way that is not married to an optimization problem. And this is where differential geometry is going to be helpful. And so, I mean, don't worry, we're not going to use very fancy differential geometry. We're mainly going to remind ourselves that one of the key features of differential geometry is that it distinguishes between points and directions, right? So in linear algebra, we would, also in linear geometry, we use vectors both to represent points and directions between 2 points. Whereas in differential geometry, we think separately of points and then vectors in their tangent space as sort of infinitesimal changes of infinitesimal directions. And the key object that connects these two is the so-called exponential map. which basically takes in a point and a direction and gives you a point that you get from walking for a unit time interval in that direction from that point. And of course, the Euclidean exponential map is maybe not so interesting. It's just you add the vector that represents the point to the vector that represents the direction, and that's what gives you a new point. And now it turns out that these barrier functions define their own notion of an exponential map, which you see here, which basically means that we use the gradient of this convex function, which for us is the sum of the L2 norm plus the negative logarithm of the derivative. We use this gradient to map to a so-called dual space that is parameterized by the derivatives of our function. Then we compute the Euclidean exponential map there, and then we map back. And so in other words, we define a new notion of a straight line that is a straight line in this sort of a dual space defined by derivatives of our barrier function. And then we just pull that straight line back to our original space. And that's how we define a new notion of straight line, an alternative way of defining straight lines. We define that in our original space. And now the punchline is that the solution path of this interior point method that I presented earlier are exactly the dual geodesics, so these modified straight lines that we have just defined. And that is great news because it allows us, or it gives us a framework for extending this regularization far beyond this very restricted setting where this minimization form is valid by simply saying we replace ordinary characteristics of the pressureless Euler equation, which were straight lines, with a new notion of characteristics, which are now these dual straight lines. And that's going to be what powers our regularization. And so now we have to do a bit of calculus. So we have our formula for these dual exponential maps. We take two time derivatives, and that gives us what you could call a dual equation of motion. So normally the equation of motion would be phi dot dot equal to 0. Now instead we have phi dot dot equal to these curvature-like terms. And so in particular, you can see if our psi is quadratic, like in the Euclidean case, then the right side drops out because you have a third derivative of psi. And so we recover our ordinary Euclidean motion. But now instead we have the sort of, we have a different geodesic equation. And then we just basically have to compute all these terms for our particular choice of deformation map. And so, I mean, it's basically this like scalar, right? So we have this squared minus alpha log of our variable. And now we just have to take three derivatives to compute all these quantities that appear here. And so we do this. I mean, this is just turning the crank. And then we plug this into our dual equation of motion. And so now we get a new equation that these deformation maps have to follow. And then we can translate the result back into Eulerian coordinates. So we reintroduce again the sort of Eulerian velocity and the Eulerian density variables, and we get a modified conservation law. And then we just add back the pressure and whatever right-hand side forces. So this gives us a way now to obtain a different or a modified conservation law by means of changing the geometry of basically particle motion. And in particular, as we'll see in a moment, this modified conservation law amounts to, if you will, a very attractive coarse graining of the effects of the shock, because basically it smoothes out the sort of like point of contact between characteristics to the sort of to this like gradual change of direction as the particle trajectories are bending away from each other. Now there's one brief sort of element that I want to kind of brush over, which is the extension to the multivariate case. So there's one sort of additional complication that basically means that is related to the fact that diffeomorphism manifolds in dimension higher than 1 are not convex anymore, so we cannot directly write down a convex barrier for them. And so instead, what we have to do is we have to view the diffeomorphisms as a submanifold of a sort of a lifted space, and then we have to compute its embedding curvature. So please feel free to ask me questions. In the interest of time, I want to kind of like brush over this. The equations unfortunately get a bit more messy than before, but I mean, the good news is that at the end, we just end up with a modified conservation law. So it took a bit of work to just compute all these guys, but once you have this modified conservation law, you can sort of forget about all these complicated Lagrangian calculations. And so here I want to emphasize that this sigma term, that is really what summarizes all these curvature contributions. So you can think of this similar to maybe general relativity, where somehow we can think of the gravitational forces as summarizing the effects of curvature of space-time onto the trajectories of particles. So in a similar way, this sigma here is a force-like term that summarizes all these curvature components nicely. And yeah, I mean, that just comes out of turning the crank. Now, before moving to the numerical results, I want to now revisit this equation from a more PDE perspective and give you some intuition for how it works. So what I've described so far, that was basically this underlying geometric picture where the equation comes from. And now we're going to look at this simply as a sort of a modified conservation law. And we can actually compare this to viscous regularizations quite directly by observing that if we gray out all the stuff that I've sort of grayed out here, then this basically becomes a viscous regularization, right? Because you have this sigma is equal to partial xu, you plug that in up there, and you basically get a second derivative of u, so you get a Laplace type operator. And in fact, we can compare it again to this this viscous regularization that I showed earlier, and we see that there are really two main differences. And the first difference is that in IGR, we have this additional elliptic problem, right? So this guy here, that, well, I guess you can't see my cursor, but yeah, so we have this additional elliptic problem that defines our sigma. And the second important thing is that in IGR, we take as a diffusion as a diffusion coefficient, we just take partial xu instead of the negative part of partial xu. So in some sense, you can view IGR really, if you want to view it as viscosity, it would be a non-local and sign indefinite viscosity. And these two features are actually quite important. So first of all, the non-locality, that is what allows us to get these smooth solution profiles. Because basically the reason why, if you remember before, we saw these sort of like kinks in the solution profiles of these local viscosity-based methods. And the reason we see these kinks is basically that if a gas particle is moving towards the shock, we are only telling it in the last possible moment to start slowing down. And that's why we see this sudden change in the velocity. Whereas now, because we have this elliptic problem that sort of propagates information a bit further, that allows us to tell gas particles to start slowing down even before they hit the shock. And that in turn allows us to get these smooth global profiles. And that's an important asset whenever we work with very low dissipation numerical methods that otherwise will still develop Gibbs phenomena. And now for this elliptic part, for the sign definite part, really the way of, in some sense, that is what helps us resolve the second problem that we observed in the beginning, which is the problem of dissipation in highly oscillatory structures. Because basically, if you now apply this local artificial diffusivity, if you apply this to this oscillatory structure, basically for every downward slope, it thinks this looks a bit like a shock, so it adds a little bit of diffusion there. And then it was systematically creates like an excessive amount of dissipation of energy, and what creates this sort of systematic loss of energy compared to the underlying numerical method. Whereas instead, if you use IGR with the same parameter as we've seen before, we do not see this smoothing out of these oscillatory profiles. And in fact, if we now increase the weight of the regularization. With the viscous regularization, the energy drops like a stone, whereas with IGR, it still stays roughly the same. And the reason here is really that we have this sign indefinite viscous, if you will, viscosity, which basically for every downward slope of our velocity, it thinks like it looks a bit like a shock, so it adds a bit of viscosity. But then for every upward slope of our velocity, we have a negative diffusivity. And so these two effects sort of get averaged out by this elliptic term, and we end up with a net zero, in fact, for this for sine type oscillation, we end up with exactly zero net energy dissipation. So in some sense, you can think of this modification as allowing to distinguish between systematic compression and sort of like non-systematic oscillatory behavior, and only dissipating energy in the former but not in the latter. And now I want to briefly, so there's a lot of work still open in terms of understanding this regularization rigorously. I want to mention that at least in the case of the unidimensional pressureless case, we can rigorously prove that when starting with CK initial conditions, we end up with global CK solutions. And as alpha goes to zero, we in fact converge to the commonly considered entropy solution for this problem. And the main, the main idea here is that we can look at this variational problem here, and we observe that it is we start by computing looking at this variational problem, and we basically use the direct method of the calculus of variations to show existence of minimizers. Then we use pseudo variations to upper and lower bound the derivatives, and then we do standard elliptic regularity plus bootstrapping in order to bootstrap our way to higher order regularity. And finally, for alpha going to we characterize the alpha to zero limit through gamma conversions of this function. Now, I promised that this has something to do with information geometry, and maybe so far you would more think that this is some kind of interior point optimization, geometric regularization, or something like that. So where does the information geometry come into play? And to this end, it's important, or it's helpful to know that one of the most important cases of these dual geodesics is actually defined on the probability simplex by the negative Shannon entropy as a potential. And this has been found in the literature on information geometry, and some of the canonical notion of a straight line to put on the probability simplex, because it is invariant under sufficient statistics, so it accounts for the statistical origin of this structure. And it is geodesic complete, meaning that we can follow a straight line forever and we stay in the probability simplex, and it's flat. So it incurs the least amount of differential geometric complications. And now it turns out that this term that we've been using for our regularization is nothing but the Shannon entropy of the mass density, right? So here on the left, we have the logarithm of the Jacobian of the flow field, and then it's just a matter of a change of variables to show that this is really just the Shannon entropy of the push-forward density. And so we maybe are familiar with the fact that the L2 geometry on deformation maps that is associated to the Wasserstein geometry on mass distribution, in the sense that if I take an L2 geodesic on deformations, that at least locally the push forward of it, that will be a Wasserstein geodesics on the push forward. And now basically what information geometric regularization is doing is combining the sort of geometry that's induced by, if you will, particle motion with a statistical geometry induced by the Shannon entropy of the particle distribution. And the idea here is, or in my opinion, really the bigger picture is to remind ourselves that this mass density is, in some sense, has this dual meaning. On the one side, it describes physical objects, right? Physical particles that we think of as moving around. But at the same time, it's sort of it's a summary of our that accounts for our limited ability to sort of keep track of each and every particle. So in some ways it ultimately has a statistical utility. And so when we are thinking about how to evolve these quantities in time, we should be aiming for evolutions that are both faithful to the physics, but that are also not crazy from a statistical perspective, that do not amount to sort of crazy jumps in our belief of what this particle distribution is doing. And that is really what this information geometric regularization does by sort of blending the geometry of the Wasserstein geometry of underlying particle motions and the sort of information geometry of particle distributions. And this has sort of like, I think, a lot of potential to be extended to more complicated procedures. So for instance, one can really view the Euler equations as arising from the Boltzmann equations by making a suitable probabilistic ansatz, the so-called Maxwellian ansatz of normally distributed particle velocities. And if we look at that again, then we see that at least for constant temperature, the log determinant that we've been using is really the entropy of this Maxwellian ansatz. And so that sort of begs the question whether we should really be introducing maybe we should be involving the full information geometry of these underlying these more accurate underlying statistical physical theories in order to regularize our equations. And so that is the sort of the big picture goal of this research line of information geometric mechanics, to basically say that normally we view the solutions of these continuum mechanical PDEs as describing some kind of a representative volume or so that that basically interacts with other representative volumes the way basically individual particles would be interacting. But instead, we should really view them as parameters of probability distribution that are summarizing some microscopic statistical physical theory. And so then we should use these sort of statistical insights to decide how should we be coarse graining them, how should we be evolving them in time. And yeah, I view IGR as sort of like a first step of making that connection, but I think there's lots of very interesting future applications of this way of thinking, especially when it comes to kinetic effects and plasmas. I think it would be very interesting to see if different ideas apply for solid mechanics, and of course, whether this sort of statistical way of looking at coarse graining, whether that also interacts in a meaningful way with, for instance, model uncertainties and the like. And I think I'm just about out of time, so I'll end it here, and I'll be happy to take any questions. Thank you.